All right, today we're going to focus on electron configurations. We're going to work on writing them, determining them where balanced electrons in atoms and ions, and drawing electron diagrams for atoms and ions as well. So electron configurations tell us how the electrons are arranged around the nucleus. It gives us the number of principal energy levels or shells as well as the number of electrons in each of them. We're going to find that each principal energy level has a maximum number of electrons that it can hold. The first PEL can hold 2 electrons, the second can hold 8, the third can go up to 18, and the fourth can go up to 32. The two that you should really focus in on just knowing their maximum is the first and second energy level. We won't tend to deal with too many that get up to 18 and 32. All right, all electron configurations on the periodic table are neutral. So if you look on your periodic table, the configuration given to you is neutral. And then when we deal with our next lesson, we'll also find out about how it's also in the ground state. So here's an example of just identifying electron configurations just by looking at your periodic table. So if we look at magnesium, its electron configuration is 282. Bromine, if you find it on the periodic table in the upper right hand, or on the right hand side, it has 35 electrons and its configuration is 28187. And then for this one we're going backwards. So I always tell students add up your electrons, get the total number, and if it's in an atom, those electrons equal the protons, which means that provides us the atomic number. And if we look up 38, that gives us strontium. So it's just very basics, being able to identify electron configurations of atoms. Now for ions, we have to add or subtract electrons from the last number in the electron configurations. So this also goes back to your understanding of ions and positive and negative charges. If we look up sodium as a neutral atom, we see it has a configuration 281. However, it has a positive 1 charge, which means we lose electrons. Specifically, we've lost 1. So that one outer electron is going to be lost, so our final configuration is just 2,8. With oxygen, which has a negative charge, we're going to then find that on the periodic table. When it's neutral, it has a configuration of 2-6. However, this negative 2 charge is telling us that it has gained 2 electrons. We're going to add them into the second shell because that can still go up to 8. And when we do that, we get the configuration 2-8. So these two ions actually have the same electron configuration, which we'll talk about further in class. But just something to start to understand about how we can write these configurations and modify them based on if it's gaining or losing electrons. The second part that we're going to go into is just understanding the types of electrons in an atom or an ion. The kernel electrons are those inner electrons, basically everything but the valence electrons that we're going to talk about. So all the inner principal energy levels. The valence electrons, and this is a really important term that's going to come up all year, are those electrons that are only in the outermost energy level or shell. So in this diagram of silicon, the 4 on the outside shell are the valence electrons. The number of valence electrons is always going to be between 1 and 8. We'll see that an atom's valence electron, if it's full, having 8 electrons, is a noble gas, and those are in the last column on your periodic table. And again, that's specifically with neutral atoms. When we get into ions, that will change. So one little thing just to kind of keep in mind, because it's going to come up all year, is that, and this isn't in your notes, so just listen for a second, noble gases are unreactive because they have a full 8 valence electrons. We call it an octet. You can think of it as almost like a happy element. They don't need to react. We're going to find out when we do bonding that they don't need to gain or lose electrons or share electrons. So they tend to be, and that contributes to them being unreactive. So elements with full valence shells or a complete octet, 8 valence electrons, are not going to easily react with other things. All right, so this is just identifying number of valence electrons. We would look up each of their electron configurations on the periodic table. So for sulfur, the inner shell, so everything but the last one, would be 10. The valence electrons would be 6. Same thing here, strontium, we're going to add up the first 4 shells, which gives us 36, and then just the outer 2 are your valence electrons. And then finally with gallium, we're going to add up all the inner shells to get the kernel electrons, 28, and then just the outer electrons are 3. You absolutely have to be able to identify specifically those valence electrons because that's going to impact a lot this year. So the reason why we care so much about valence electrons is that they really determine the chemistry of our atoms. So we represent them with something called Lewis or electron dot diagrams. The kernel, all the inner electrons, the nucleus is represented by the symbol, and just the valence electrons are represented by dots, or sometimes X's. We're going to write the element symbol, we're going to look up the last number in the electron configuration, and then we're going to place those dots around the carbon. Usually you want to try and put them kind of like on each side. If you think about a box being drawn around carbon, we tend to put the first two together and then we spread out the remaining ones kind of going around the symbol. So carbon has a configuration of 2-4, so 4 valence electrons, which is why we have 4 dots on the carbon. If we're working with an ion, we're going to have to adjust those valence electrons. You're also going to see that we have to use brackets and charges and place them in the correct spot. So sulfur, which has a -2 charge, means that it's gaining 2 electrons. So we're going to have to add those 2 electrons. If you look up the configuration, it has 6 valence electrons normally. So if we add to that, we're going to end up with 8. So we place the sulfur, the S, in the center. We have the 6 that it originally had, plus 2 additional ones, so it ends up with 8 electrons. We put brackets around it, and then we put that charge on the outside of the brackets. We're going to find that negative ions are always going to end up with 8 valence electrons, so if you can remember that, it definitely saves you some time. With potassium having a +1 charge, this has lost 1 electron. So potassium is going to have to lose 1 electron. It only has 1 valence electron if you look up the configuration on the periodic table, which means it actually has no dots around it. It has electrons in the inner shells, but at that point the valence shell has been cleared out. We can put brackets around it. This is one that you actually don't have to. Some students prefer to do that just so they're being consistent, and then the charge goes on the outside. We're going to find that positive ions are always going to end up with 0 valence electrons showing, or dots. And that's it. We're going to spend a lot of time tomorrow going over Lewis dot diagrams and electron configurations, but this just gives you a little background to get you ready for that.